Yeah, let's go. The bus trace system, automating bus traffic debugging in IP-XACT based SoC beyond the traditional debug method. Abstract. The bus trace system (BTS) is a novel debugging approach for system on a chip. Its verifications based on the IP-XACT. BTS aimed to automatically identify and debug bus hang errors and error responses using only signal simulation logs without the need for waveform information. BTS works by utilizing the SoC bus navigation information that is generated through an in-house bus connection searching algorithm, which searches IP-XACT to find the full bus connection for each instance. By analyzing the interface logs connected to design under task DUT, BTS can identify the scope that needs to be debugged. By using BTS, the debug time and verification turnaround time (TAT) can be reduced, as it automatically finds the bug scope related to bus hang and error response in SoC verifications, so that it can help to decrease the verification time speed during overall SoC development. BTS is a powerful debugging methodology that can effectively reduce the debugging time in trend of the increasingly complex SoC architectures. Section 1 Introduction. Over the past few decades, transistor densified per single chip has increased exponentially due to the continuous advancements in process technology. While in the past only 1 to 5 million registers were integrated, this number has increased to over 5 million and more recently. Over 12 billion transistors have been integrated. So in addition to the emergence of new trends such as current design and multi-core system, 3D integration and multi-chip integration, SoC architecture is becoming increasingly complex. This means that the verification engineers are spending more time debugging during the SoC development. Statistically, the mean peak number of verification engineers in SoC project has continued to increase up to 11.6 billion in 2016 from the 4.8 in 2007. At the same time, only 47% of the time per SoC project was spent on verification in 2014, but this increased up to 54% in 2018, and this trend continues. So the building time is that increasingly and becoming a critical factor in development SoC. In SoC architecture, the communication among the intellectual properties IPs takes place through the internal bus. Due to the advanced in process technology in both number of the IP interfaces and count of the internal bus node instances have increased, so resulting in a heightened complexity of the SoC structure. This has particularly resulted in the more debugging time, especially in error cases such as bus hang and error responses. Because this is due to the fact that a conventional debugging approach involves tracing all of the buses to identify the initial point of error occurrence. If verification engineers have limited understanding of overall SoC architecture, the time required to debug these errors can become even longer. For example, in a SoC, when a master accesses a slave through 10 bus nodes and a bus hang occurs where the master does not receive a response, verification engineers must check all bus nodes to identify which one is causing the problem. In this case, if it takes t time to check one bus node, and then in the worst case, it takes 10t to check all the bus nodes. Particularly in the process of checking all bus nodes, those that operate as expected do not require verification. If the problematic no bus nodes are identified in advance, unnecessary debugging time could be eliminated. However, the challenge lies in quickly identifying which bus node has a problem at a glance. Even engineers with extensive verification experience find it difficult to find the problem nodes in a first glance. Identifying the probability bus nodes promptly can significantly reduce debugging time for errors such as bus hang and error responses. The bus trace system (BTS) aims to effectively reducing debugging time by automatically identifying the problematic bus nodes and reporting to the engineers. BTS generates bus connection information known as SoC bus navigation from the master instance to the slave instance using an in-house connection searching algorithm to automatically identify the problematic bus node. When the navigation information is created, BTS periodically analyzes logs during the simulation to determine the scope of debugging required in case of the error occurrence. When the BTS detects abnormal behavior, such as a bus hang and error response in the log, it identifies the debug scope and reports it to the engineers. Our proposed methodology utilizes BTS to automatically identify the debug scope for a bus hang and an error response, thus providing a fast and efficient debugging process to verification engineers. So the figure 1 illustrated the overall operation of the BTS, which is divided into phase 1 and phase 2. During the phase 1, and SoC bus navigation is created using an in-house bus searching algorithms from IP-XACT based on SoC integration information. Phase 2 involved connecting system value interfaces to the DUT to obtain the bus traffic log during the simulation. The simulation log is then periodically monitors and debug its performance when a abnormality is detected. Ultimately, the probability bus is reported. Phase 1 makes SoC bus navigation. The phase 2 automatically finds a debug scope during the simulation. So the figure 1 is the BTS overview. Section 2, the BTS processing. Phase 1 generates SoC bug in navigation information. To automatically obtain the bus connection information from master to slave, we created a SoC bus architecture in a format that can be handled by the Python script. First, we converted the IP-XACT based SoC integration information to a JSON file via Magellan Tools export utility. The ledger JSON file contains information about the bus connection, ports, and interfaces. To determine the instance connected to each instance of the bus routing logic, which has many interfaces, we used the SoC bus integration specification file as input to execute a Python script, resulting in creating the JSON formatted bus routing specification file. Additionally, a Python script reads our SoC level UVM register base address system value file to generate a separable base address JSON file for each IP. Once these steps were complete, we learn a Python script that takes 3 files as input. The script includes a bus connection searching algorithm and bus navigation generating to create a SoC bus navigation as a JSON format. Additionally, in this phase, BTS generated a set of key interface information for each bus protocol, including AXI and ACE, the CHI, and its custom protocols. This key set of interface information is used when a BTS detects connectivity information between interfaces. A bus connection searching algorithm. To begin with the connection search, the interface must be determined. In this paper, we chose the host CPU interface as a starting instance and used the UVM register modeling system value specification file to generate a list of final Destination instances. The algorithm uses reference inter-instance interfaces, iterative searching for instances adjacent to the interface of each interface instance from the starting instance to target instance. Once the starting instance is determined, the bus protocol types of the interface is checked first to search or pass of bus, conducting the actual searches for valid bus connections. The algorithm then is retrieved from the interface information from the JSON file extracted during the phase 1-1, referred to the figure 1, using each node instance name. It identifies the instance's key interface and the bus protocol type. If the key interface is found, the algorithm uses it to identify its corner instance and the target instance connected to the key instance. As an example of this searching algorithm illustrated in Figure 2 for AXI slave instances, we define the miscellaneous _m interface as the key interface for the AXI protocol. Therefore, the interface connected to it is identified as a counter interface. The instance that has a counter interface is thus determined the counter instance in our algorithm. The counter instance then becomes the starting instances and the algorithm recurses the process, and when in the current counter instance is just in the list of the final destination instances. If the counter instance is in the list, the search is terminated and the row bus navigation file is created. This is called a row because the SoC bus routing specification was not considered in this step. As such, the row bus navigation file may contain incorrect information that must be rectified before use in a simulation. The Figure 2 is a process of creating a row bus navigation file. B. Bus navigation generator. To extract only valid information from the row navigation file, the bus routing specification file must be utilized. The bus routing specification file contains the bus routing specification for each interface of an instance. However, even if the Python script knows the bus routing information for each instance, it still needs to know which base address to route to. Therefore, in this step, the script retrieves the connection information from the row navigation file and initiated a new search that includes bus routing information for each final destination instance's base address. By defaulting to this process, the extract counter instance can be identified. Similar to the process of creating the row navigation file, the counter instance becomes the starting instance again. The process is repeated recursively if the counter instance is the final instance list. And the research is terminated and a final bus navigation file is created. The Figure 3 illustrates an example of determining the counter instance using the routing information from an instance that supports bus routing features. In this example, the Python scripting file must specify the target IP base address. So next, it initiated a new search based on the row bus navigation file from the starting instance. If the current instance is a bus routing instance, the script checks the routing address range for each instance interface of the instance and determine the counter interface instance. The Figure 3 is an example of determining the counter instance at the bus routing instance. The Figure 2 automatically finding a debug scope during simulation. To detect the abnormal state in the simulation, such as a hang and errors response, we found the test-specific system belong interfaces to all the DUT internal interfaces during simulations and exported observed data as a log file. To generate the test bench interfaces, we used the JSON file extracted from the phase 1-1 figure 1 and find all masters and interface information in the file. Next, we define the representative interfaces for each bus protocol, such as CHI and AXI and ASU and custom bus protocols, and created the interface instance for all the masters. Within each protocol-specific interface, there are bus protocol inspectors internally. These inspectors have been developed by modeling each bus protocol in the system value. So the inspectors include a bus protocol handshake detector that detects only valid transactions, a traffic burst length inspector, and include time logic to detect bus hang. The inspector outlaws periodically that meet the specifications of each protocol during the simulation. Afterward, we bound all generated interface instances to our masters before simulation. When a simulation starts, bus protocol interface logs out from all connected interfaces. If a log file is created for each master interface, a large number of files will be generated, and we have determined that this approach is highly inefficient. Instead, we have generated individual interface log files for each bus protocol, such as AXI, AXE, ACE, and CHI, and so on. Subsequently, only valid traffic detected by the interface is outputted to the respective log files in chronological order. Log files are generated individually for each bus protocol, such as AXI and JSON, CHI JSON, and ACE JSON. So plus these interfaces also have a timer logic to detect bus hang. Figure 4 illustrates the overall process of extracting valid bus protocol logs during the simulation. Figure 4, the process of extracting a valid bus protocol simulation log. To analyze the log, concurrently with the simulation, a separate Python script is executed with the start of the simulation. This script activates in the event of the bus error response in the log, or if the log stops printing while the time reaches a certain threshold. Its purpose is to identify the problematic area of the system and generate a debug scope. First, the Python script retrieves the bus connection information from the bus navigation file based on the traffic address information. Next, it tracks the traffic trace in a log, starting from the end and working backward. The reason this approach is more efficient data starting from the beginning that it excludes the traffic that already been processed. If the traffic were to be traced sequentially, it would be an inefficiency as it would review the traffic has been processed normally. On the other hand, by tracking the flow of the traffic in reverse and quickly identify the most recent problems and avoid unnecessary traffic review. As a result of this tracking, the Python script reports the problematic instance to a verification engineer. Figure 5. So the figure 5 illustrates an example of using BTS in a SoC to identify the instance causing bus hang when the master issues the bus traffic but receives no responses. After BLK_CPU does not receive a write response from IP_A for an extended period, despite issuing a write transaction on a OS 1083_0808 and the timer exceeds the threshold of a log stops printing, BTS is triggered to debug this abnormal situation. The BTS first calculates the IP address of the problematic traffic. This is because the created bus navigation for each IP is based on the IP-based address. In this example, the calculated base address is OX1083_0000. Next, it received the bus connection information corresponding to the OX1083_0000 from the navigation files. Then BTS tracks the write traffic associated with the OS000808 in the interface log, starting from the last instance in the bus connection information list. As a write response will be issued from the last instance to the start instance, the last write response to login interface logo was printed in the bus_family_2, suggesting the bus family 1 did not respond to response via K_CPU. Therefore, the bus hang point is identified as a bus family_1. Consequently, the BTS reports the bus hang instance name to the verification engineers via the terminal. Figure 6 shows the debugging region of BTS for the bus hang related to the traffic associated with this address. This address OS10X0X0X0808 and address as printed as the terminal. So this is the figure 5, the workflow for this is covering the simulation hang point. And this is the user wrote terminal, and the figure 6 is terminal view seen by the user when a UPTS is executed. So section 3 is experimental leisure. We have identified bugs such as the bugs hang and the error response that can be easily fixed using the BTS in our recent 3 SoC project. Table 1 shows the number and the ratio of the errors that correspond to the bus hang and the error responses among the all reported bus cases in our 3 SoC project. Although the error ratio varies for each of the 3 projects, it is noteworthy that these errors account for the approximately 10 to 12% of the total errors. These suggest that around 10 to 12% of all errors can be identified with the BTS. We also analyzed the frequency of these errors throughout the entire SoC project period. Figure 7 shows the cumulative occurrence rate of the bus hang and the error response hangs for each of the 3 SoC projects during their respective evaluation period. This is calculated by converting the errors count mentioned in table 1 into a percentage. For all 3 projects, at least 50% of the total error cases occurred before the milestone of the implementation started during the overall SoC development period. This generally indicated that such bugs were preliminarily concentrated and occurred frequently in the early stage of the project schedule. Even when viewed based on the start time of synthesis, a bug occurrence rate of more than 50% can still be observed. Detecting as many bugs as possible before the start of the synthesis could potentially shorten the SoC development schedule. This is because the synthesis stage holds significant importance of the overall SoC development schedule. Bugs discovered after this stage can affect the synthesis process and may even require the resynthesis, leading to the potential delays in a layout schedule. Applying BTS in a SoC verification is beneficial as it allows for not only the accurate and easy detection of bugs, but also a reduction in bug time. Moreover, the achieved quick stabilization of the bus integration before the start of synthesis can ultimately help to shorten the SoC project schedule. Also, the bus hang bug can create a bottleneck which may delay the identification of other bugs such as IP malfunction and security violation and etc. However, through the rapid bus stabilization, these bugs can also be identified quickly. Table 1 is the number of bugs that can easily identified using BTS in 3 SoC projects, and figure 7 is the occurrence rate of errors such as bug hang and bus error response during the entire project period, and the bugs occurring right up to the start of implementation in 3 SoC projects. Next is for the conclusion. BTS is an effective and user-friendly system for debugging bus hang of errors and 3 error responses, which frequently occur before the synthesis begins due to the unstable bug integration of SoC. The verification engineers often spend a considerable amount of time debugging these bugs because they have to check all bus nodes to find nodes where the problem first occurred. The engineers with less verification experience may require even more time to debug these bugs. However, BTS can quickly identify and debug these bugs, and therefore using BTS during the SoC development can significantly reduce the time required for verification. So to quickly stabilize the SoC bus architecture, and it can lead to a shortened SoC development schedule. As a result, BTS can be fast debug methodology in increasingly complex SoC architecture trend. Okay, thank you for your time today. I read this DVCON2024 paper, Bus Trace System, Automatic Bus Traffic Debugging in IP-XACT based SoC beyond the traditional debugging method. Thank you again for your time and see you next time. Thank you.